The award-winning Miss Franklin will have a place in our lecture today, hopefully. Later on, you'll see the connection. So I'm going to start today. We are going to talk about minimum spanning trees, the problem that we introduced last class. It is a greedy algorithm. Here is the setup of the problem. So imagine you have some sort of network. You have a bunch of houses or routers or so forth. And what you'd like to do is make sure that in the case of this little village, that each of the houses in that village were connected. So from any house, you could get to any other house in that village. And so therefore, you need to build a road network between these houses. And the constraints are that you want to spend as little of your city's money in building roads. And so the way you're going to solve this problem is you're going to represent this little village as a graph, something like this. These are all the possible roads that you might be able to build. And now you'd like to find a connecting tree or a spanning tree for this particular graph. So remember, we're going to, if you need a review of graphs, there's CLRS chapter 22. But basically, a graph is going to be a set of vertices and a set of edges. These edges are going to be basically pairs like UV from V squared. In last class, we discussed several ways of representing graphs, either adjacency matrices or adjacency lists. And the other component of a graph that we'll use in the next few lectures is a weight function. And this maps each of the edges to positive numbers. So this is the edge weight. It's very useful to give weights to edges. For example, in our city problem, these edge weights right here represent the cost for building that particular link. You can have these edge weights also represent, for example, the speed of that link if you're talking about a communication network. Later, we'll also add capacities if we want to represent, for example, how much material can pass over that edge, at what cost and at what rate, etc. But today, we'll just have weights. Now, the nice thing about, so graphs are very nice combinatorial objects. We'll study them for the next few lectures. A key property of a graph, or a key object that's related to a graph, is a path. And the path is just a sequence of nodes, like V1, V2, all the way up to Vk, with the property that each consecutive pair of vertices in this sequence is an edge in the graph. So there are many kinds of paths. The paths that we care about most are simple paths. Simple paths are one in which each Vi occurs at most once. A simple path is one in which each vertex appears at most once in the path. So you don't have to have the vertex in the path, but if it appears at most once. In other words, you don't have V1, V2, V1, V2, V1, V2, V1, 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 etc., something like that. And a cycle, this is a path of length 2 or greater, such that the end is also the beginning. So another way of thinking about a simple path is a path that doesn't have any cycles in it. So let's get to, we're doing all of these definitions to help us precisely figure out what we want to compute in this problem. And a connected graph is going to be a graph such that for any pair, for any two vertices in the graph, so a connected graph is such that for any two vertices in the graph, there exists a path between those two vertices. In other words, there exists a path that starts at U and ends at V. Right? And if we have that notion, then we can call a tree, something I think most of you are familiar with. A tree is simply a connected graph with no cycles. So what we want, if we're given a graph, which is equal to V, comma E, comma W here, what we want to do is we want to find a tree that's a subgraph of this We want to find a tree that's a subgraph of the graph we're given that has the minimum cost or the minimum weight. Okay, so we're looking for a set of edges such that that set of edges connects all of the vertices, and it has the least cost. And cost is just going to be the sum of all of the edges inside our tree. So this is a problem that has been studied since at least the beginning of this century, 1900s. A very notable solution, this Hungarian Berufka, when you take the graduate version of this class, we start lecture 2 with his solution and develop ways of extending it into faster and faster ones. So at least for the last 100 years, this problem has been studied because it relates directly to these type of transportation or communication networks. And we're going to study 2 particular solutions. And we're going to study them in this general context of a greedy algorithm. That, so to start developing our first greedy algorithm, I want to identify a few properties the solution is going to have. So these questions, I think, are out of order. We talked about last class how a minimum spanning tree, meaning a solution that satisfies these things, it shouldn't have any cycles. Does anybody remember why? A cycle is essentially a redundancy. So you don't need them because they won't add to connectivity and they'll just cost in terms of the edge weight. So there are no cycles in our solution. So this particular relies on the fact that we're assuming all of these edge weights are strictly positive. So let's just say that all of the edge weights are strictly greater than 0. And the other property is, how many edges do you think a solution has to have? Yes. Why? Yeah, exactly. One edge connects 2 vertices, right? So in a tree that doesn't have any cycles like this, you know your solution has to connect V edges. So even if it's not a single line, you know that starting from some particular node, an edge basically adds 1 extra node to your connected component. So you're going to have V minus 1 such edges in order to connect all V nodes. Okay, so these are nice properties. And in fact, these are enough properties in order to suggest our first strategy, also known as Kruskal's algorithm. And you start with an empty set of edges. You know that you need V minus 1 of them. So all you do is figure out what the lightest edge that you can add to your set A that doesn't create a cycle is. Find that edge and add it to your set. And after doing it V minus 1 times, you'll end up with a solution. I think we went through this example in last class. I'll go over it once more. So we start with an empty set of edges, and A is, in fact, this edge right here. 1 is the lightest. And then we continue by adding the lightest edges that we can that do not produce cycles. In this case, 3 would produce a cycle, so we don't add it. But 5 does not produce a cycle. 6 does not. These 2 do not. This 9 would create a cycle. This one right here. This 9 would create a cycle like this. And so that is our solution. Right? And those are the steps. So the question that we should think about for this class, that was basically a recap of last Thursday. Why does this solution actually work? Very simple 3-line algorithm. Why does it work to find the minimum spanning tree? So this is what's going to happen in the next part of this lecture. We are going to define a few more properties that help us get at the underlying reason for why this algorithm works. Then we're going to generalize that insight and find another algorithm that's actually easier to implement than this one. So just like I've been telling you with these greedy algorithms, They are, in fact, very easy to implement, or at least they're conceptually very simple like this. But the reasons why they actually work are somewhat more subtle and require more thought. So, a cut is basically a partition So a graph cut is a way to partition the graph into two sets, S and V minus S. Okay, so here's an example of a cut. I'm going to make this right here. I'm going to make this S, and I'm going to make this the rest, which is V minus S. Right? So the partition need not have any constraint about it. It's just a two sets that add up to make V, and they're disjoint sets. So now what does it mean to cross a cut? So an edge is going to cross a cut if one end of the edge is in one side of the partition and the other end of the edge is in the other. Your question, so can you push the green button? Let's see if that works today.
So you said add the lightest edge that doesn't create a cycle.
Yes.
Are we specifying how to check if it cycles, or? Very
good. So this is what I said about we're going to generalize this to find something that's slightly easier to implement. So a very good question is, how can we actually check whether an edge is going to create a cycle or not? And the accepted answer for this is you can come up with many solutions. The most efficient and actually the one that's used in Kruskal implementation, you use a special data structure. It's called the union find data structure. And it is an excellent data structure, and we're going to try to cover that in a few lectures when we actually get into the data structure portion of this class. But for today, let's just gloss over how to actually check for whether adding an edge creates a cycle. And in fact, the solution that we're going to come up with is going to be based on priority queues, a simpler data structure that we'll talk about. So again, the plan is we're going to talk about Kruskals. It's the easiest minimum spanning tree algorithm to think about, but slightly more difficult to implement because you need a fancy structure like this. We're going to figure out why Kruskal actually works, and then use that same reason in order to come up with an easier implementation. Actually, the one we're going to come up with is going to be called Prim's algorithm. So crossing the cut. Here is an example right here. This is S and this is V minus S, so the cut is depicted in these pictures right here. And any of these edges right here are edges that cross the cut. Does that make sense? Here is another example. Here's the example we started out before. And now, can you tell me which edges actually cross the cut here? Remember, this was S. The other nodes were V minus S. Which edges cross the cut? Help me depict them. So GI, GH, GF, HD, yeah. This one, this one, this one. Those are the edges that cross the cut. Good. Everybody has the idea. And now, wait, any more? And now comes Miss Aretha Franklin's contribution to this lecture, which is what it means for a set of edges to respect a cut. Okay? So a set of edges A is going to respect the cut S, V minus S, if no edge in A crosses the cut. Okay? So this is an important concept. I'm going to put it on the slide. It's going to be the key to R. This is the main idea. In the graduate version of the class, we jump right to the not so simple versions of this algorithm, which make use of some other properties. Question? The purple edges there, those are just edges which cross the cut. A cut is a partition of the vertices. So the cut is only going to talk about the vertices of the graph. The purple edges are just examples of edges that cross the cut. So the cut theorem. So it's a lot to set up with this theorem, but once you get the intuitive notion, it's quite a simple property. So what we're saying is, suppose you have some partial solution to the MST. So you have some subset A of some minimum spanning tree. And by the way, that subset can be empty. Consider any cut such that A respects that cut. So after you have A, you have some partial solution, you get to pick a cut. As long as A respects that cut, you can pick any cut. And now consider the lightest edge which crosses that cut. That lightest edge you can add to your partial solution and be guaranteed that what you have is going to be part of some minimum spanning tree. So if you have some partial solution, this is a rule that allows you to grow that partial solution into one that's slightly bigger, that has one more edge in it. Do you see how this relates to all of the other greedy algorithms we've talked about? The scheduling problem, the Huffman coding. All of these problems you have some partial solution, and you have some rule for extending that partial solution little by little. Question? Nope. A is just part of a minimum spanning tree of the original problem, of the original graph. You have some partial solution. You're working towards a final one. It's a partial solution. To find an edge to add, all you have to do is define some cut such that A respects that cut, and take the lightest edge that crosses it. So we have two things to do. First, argue why this theorem is true. And second, argue why Kruskal is making use of this theorem. This is why Kruskal's theorem actually works. Okay, so let's consider an example of the theorem just to get our intuition straight. So remember, in Kruskal's algorithm, we were at the spot where we had taken this edge and this edge. Okay? So A is going to be essentially the edges in orange. And I'm just going to redraw this graph so that the cut theorem becomes a little bit clearer. So between these next two slides, all I've done is taken these orange ones and put them in a straight line on this side, on the right side, and the rest of the nodes are on the left side. So this is A right here. And now, what does the cut theorem say? It says, pick some cut SV minus S such that A respects the cut. How will I do that? Well, let me tell you how I'll do it. I will pick this to be S. So A is going to be S. And notice that it just so happens that A respects this cut because all of the edges are inside S. Okay? And now what does the cut theorem tell us? It says, let E be the min weight edge across this cut. Which edge will that be? In fact, there are two of them. We can pick either of them. Both of them are min weight. Let's pick that one. And now the cut theorem says that these three edges are now part of some minimum spanning tree. Question? So the cut theorem says we can pick any cut. And in fact, you're foreshadowing what we're eventually going to do. So the cut theorem says we can pick any cut. Kruskal is just going to happen to pick cuts that look like this. And the way the cuts are chosen is going to define the edges that we're going to add. We'll talk about that in just 3 slides. Your observation, I think, is, well, could we have picked another cut like this, this, and that? And in fact, if Prim's algorithm, all Prim's algorithm is a different rule for picking cuts. Everybody see the point of this example, how we were able to extend the thing by 1. Okay, so then, this is the cut theorem that we would like to prove. And you can follow along here on that diagram right there. Okay, so what exactly do I want to say here? So here's how the proof is going to begin. We're given some partial A. We've identified some edge E. And now we need to reason about A union E. If it happens that A union E is already part of the minimum spanning tree that's defined, if it already happens to be the minimum spanning tree that we have in mind, then the theorem is going to follow. Right? So if I were to say this theorem, suppose the set of edges A is part of an MST T of graph G is like this. So this would be the full statement of this theorem. Okay? So if AE is already part of the minimum spanning tree that we've identified in the theorem statement, then the theorem follows. If it's not, we're going to do like we did in Huffman and like we did in the scheduling problem. We are going to construct another minimum spanning tree such that this property does hold. And this is going to follow an exchange argument. We're going to exchange whatever the solution has, we're going to exchange RE. We're going to put RE in, take something out, and argue that we still have a minimum spanning tree. So let E equal U comma V. So if we were to draw a diagram, here's what we might say. So let A is going to be the orange links. T, which is the MST, is going to be blue plus orange. Okay? This is the edge E, which connects U and V. Okay? And we also know that S comma V minus S is a cut, and A respects S. So here's what we're going to do. First step, add E to T. What happens when we add the edge E to T? T was a minimum spanning tree. In this diagram, edge E connects U and V. What happens when we add edge E to this tree? You make a cycle. A cycle is created. Let E prime be the first edge. And by the way, a cycle is created from U to V to U, right? Because edge E connects U and V, the cycle is going to be from U all the way back to U, right? So let E be the first edge on this cycle from U to V back to U. That crosses. So in this case, which edge is E prime? Which is the first edge to cross the cycle if you're going from right? Is everybody following? Question. Yeah. Let E be the first edge on the cycle from E to V to U that crosses V. Yeah, let me say this in a different way. Good point. So the question is, why isn't E the same answer? And I want to define it so that E prime is going to be like the first edge that's not E. But how do I define that properly? So what I want to do is start from U, take E across, so I'm on the other side of the edge, other side of the cycle, and now find the first edge, E prime, that's on the path back to U. So that gets me out of this pickle. Thank you. Okay. Second point. Do you see what we're going to do now? Consider the tree T prime, which is equal to T, minus, we're going to subtract E prime, and we're going to add E. Spend 2 minutes with your neighbor explaining that T prime is an MST. So this is, I want you to put the reason right here for why. In fact, if you're following along in that handout, you should be writing this proof. Why is T prime an MST? 2 minutes with your neighbor. What are the weights between E and E? What are the differences in the weights between E and E prime? Now, adding this edge and taking away E prime, does it change the connectivity of the graph? So, first I want to argue that it's a spanning tree. Well, first it has no cycles because when we added that one edge E, that created one cycle, and we broke that cycle. And we also know that the set of edges, the number of edges in T prime, is also V minus 1. So it's going to maintain the connectivity. Since it has V minus 1 edges and no cycles, it's still going to be a spanning tree. Now let's consider the weight of T prime. That's going to be the weight of T minus the weight of E prime plus the weight of E. Now I'm going to argue that this is going to be greater than or equal to, and that's because the weight of E is less than or equal to the weight of E prime. Why is this last sentence true? Yeah, in the back. That's right. E happens to be the lightest edge that crosses this cut. And so both E and E prime cross this cut because E was chosen that way by definition, and E prime was the first edge on this cycle that crosses the cut. So since T was an MST, this implies that T prime has to be an MST. In other words, this has to hold with equality. And of course, as you can see, both of these edges had 3 in this case. Well, the only point that we're going to be using here is the fact that when we selected E from the theorem right here, right? E is the edge with the is on edge with the minimum weight that crosses this cut. So that's all we know. That E is the edge with the minimum weight. E prime is some other edge that crosses this cut. And if it was in fact part of a minimum spanning tree, it has to have the same weight. But we don't need to use that fact for this proof. Does that make sense? Stronger, yeah. Question in the back. Just like with Huffman, and just like with the scheduling, it's possible for there to be more than one minimum solution. Right? With Huffman, we saw there were 2 codes that had the same sort of weight. Similarly here, there could be 2 minimum spanning trees. We're just giving an algorithm that finds one of them, that finds one. There can be more than one, yes. Especially if the edge weights are not all unique, like in this case. Now, with this cut theorem, which is right there, I think we now have the tool to understand why Kruskal's algorithm is correct. Okay? Because in the step 1, A, in step 1 of this algorithm, we start with A as a subset of some minimum spanning tree. So this proof is going to be by induction. So we're going to say, suppose after k steps, A, so in particular, on the first step, k is going to be 0. After 0 steps, A is the subset of some minimum spanning tree. Of course, we start like that, and after k steps, let's suppose that we're also like that. Now consider one iteration of the loop at 2 and 3, at lines 2 and 3. So let E be the selected edge. I claim that there are going to be 3 cases. Is everybody okay with this part of the proof? So the 3 cases are going to be as follows. Either both U is going to be an A and B is going to be an A. So suppose that these green parts right here are what A consists of, right? The orange and green is what A is. There are going to be 3 cases. The first case is that both ends of both U and V happen to be an A. The second case is just U is in A. And the third case is neither U nor V are in A. Everybody agree that those are the only 3 cases? Okay. So let's consider the first one. Case 1. U and V are both in A. So what I'm going to do is I'm going to take S So if U and V are both in A, I'm going to take, this is U and this is V. I'm going to take every vertex that is connected to U so far by the edges in A, and I'm going to call that S. And this, of course, whatever this in the rest of the graph is going to be V minus S. There are other nodes which I haven't depicted here. And now what does the cut theorem tell us? A respects V minus S because the way that I've constructed S is to take every node, every vertex that is connected to U. So every edge that possibly emanates from a component from U is going to be already in S. So then, by the cut theorem, E will also be part of some MST. Let's consider the next case. So ignore this part right here. That's case 2. U is in A, but V is not. How should I define S in this case? Speak with your neighbor. How should S be defined so that we can use... What is our goal? Our goal is to argue that the edge... So notice Kruskal is going to add some edge to our solution. We want to argue that this edge is indeed going to be part of our solution. The way we're going to argue that is by using our cut theorem. So we say, well, consider what we've gone through. After k steps, A is part of some MST. We're going to add some edge to A. Well, that edge can either have both of its endpoints in A, one of its endpoints in A, or neither of its endpoints in A. We've already handled case 1, and now case 2, one of its endpoints is in A. We want to apply the cut theorem. With your neighbor, try to figure out what we have to do to finish the argument. So in this case, we can set S to be the entire set A. Because in particular, this edge E is going to cross, it has one of its endpoints in A, so therefore it has one of its endpoints in S, which means the other endpoint is not in S. And so E is clearly an edge that crosses this cut. And now it's also going to be the edge, the lightest edge which crosses this cut. Why is it the lightest edge? No, there could be other edges that cross this cut, right? I haven't drawn them, but there could be other edges which cross this cut. But how did we pick edge E in Kruskal? Remember, the selection parameter in Kruskal's algorithm is pick the lightest edge which doesn't create a cycle. That's a very nice, clean way of saying it. What's also true is it's the lightest edge which happens to cross a cut which respects your partial solution. It's just a longer way of saying it. But it's the reason for why it works. Because it is the lightest edge. Right? It doesn't create a cycle among the edges that we've selected so far. And so that's why we know that we can define this edge in that particular way. And so therefore, by cut theorem, the final case is in this case, when neither U or V are in A, and in that case you can define S to be just U. Right? Again, A respects S because it only contains one. And E is the lightest edge. So this is the intuition for why this algorithm works. Question? In this diagram, so if you were to say, not just this green part, yeah, the connected component that the component that contains U, right? You start from U and consider all edges that come out of it. And in that case, A would also respect S. And so that would work as well. You'd have to make an extra, yeah, that would work. Yeah, in fact, I do like that. Okay, so that's why it works. Because that lightest edge that we select can fit right into our cut theorem. Now, the analysis that you pointed out earlier is how we actually implement this right here. And one can, in fact, use a pretty efficient union-find data structure to do that. But that is a complicated data structure. Or at least it's an advanced structure. Has anybody implemented or seen this union-find before? You don't see it in 2150, right? Okay. We'll talk about it later in class. You'll sort of see why it's a nice, elegant data structure. But today, I want to sort of not introduce that structure. I want to consider a different algorithm that doesn't require such a fancy data structure. And so consider this general minimum spanning tree, right? Kruskal was a specific implementation of this idea. Start with the empty set, pick some cut that respects A, find the smallest edge that crosses the cut, and then add this, right? This Kruskal is one instantiation of this general strategy. And now we're going to consider another instantiation, which can be implemented with just a priority queue. Very simple data structure. How are we going to do it? So this is Prim's algorithm. And Whereas in Kruskal's algorithm, A is just some arbitrary set. In Prim's algorithm, we're going to maintain the invariant that A is always a tree. So A is connected always. And E is going to be the lightest edge that grows this tree. All right, so let me show you diagrammatically how Prim's algorithm is going to work. We're going to identify some starting node. Now, our set A is going to first start with this D right here, this one node, and we're going to always maintain A as a tree. So we're going to grow this tree. Consider this node D, and now look at our first iteration of the cut theorem. We're going to set this right here, just the set S, which has this node D. And now, what is the lightest edge which crosses this cut? It's going to be this 5, right? So that is how we're going to make our first decision. We're going to set S to be this thing, and then we're going to find the smallest edge which crosses this cut right here. And so this is the next step of our algorithm. Again, we are going to set S to be the current solution. In other words, S is always going to be A. Another way of thinking about this solution, whereas in Kruskal's we had those 3 cases of how to set S, here we're going to maintain this invariant that S is always going to be the solution that we currently have. And so now if S is these 2 nodes, what is the edge, the lightest edge which crosses this cut? Okay, so clearly, yeah, so the next step would be to extend along this edge right here. And now you can see, again, S is going to be now these 3 nodes, and the lightest edge which crosses this cut will be, which is the lightest edge which crosses this cut? The 1, right? So we'd extend along this way. And so forth, until we get the same solution in this case. Okay? So the idea is going to be S will always be the current solution S, and we can use a priority queue to help us determine the min-weight edge. So we can use a priority queue to help us determine the minimum weight edge that crosses the cut that crosses the cut S B minus S that we're maintaining. Okay? And so let's get into some slight more details about this. So let's start with the priority queue. So a priority queue, it's going to support a few operations. Insert, extract min, and decrease key. So the insert operation inserts a node into the tree. Extract min returns the smallest element that's in this tree. And decrease key, if you give it an element that's already there, so if you have some element E and some lower key, you can reduce the weight that a current node currently has. I think all of you are familiar with these priority queues. You studied them in 2150, right? Okay, so let's just do a review. Typically, we're going to represent priority queues as binary heaps. So they're going to be like binary trees that are as full as they can be. So only the bottom row has empty leaves in it. And now if we wanted to do, for example, if we wanted to add a node to this tree, like suppose we wanted to add a 9 to this tree, then we go to the bottom row and find the first empty slot. So in this case, it's going to be right here. And we go ahead and put that node in there. Now the condition that we want to satisfy with this binary heap is that so your key value has to be smaller than either of your children's key values. Right? That's a property that you're familiar with. In this case, 4 is smaller than 21 and 6, et cetera, right? So if we add a node at the bottom here, we may not continue to satisfy this property that a key should always be smaller than its children. In this case, 24 is not smaller than 9, which is its child. And so we can fix that by simply swapping. So once we've added 9, we can continue swapping 9 with its parent until this property is held. Right? So in this case, we swap 9 with 24 here. And now 9 is still smaller than its parent, 21. So we can do another swap. And then at this point, 9 is larger than its parent, so it's fine. Can someone explain to me how you do extract min on a heap? Yep, you take this guy out. Good. Now you have a hole in your tree. What do you do? What do you do? Well, yeah, so remember the other property that we're maintaining is that it's a full tree. So we take this last guy and we put that last, we promote the last guy in the line there. And then recursively push this guy down. So 24 is larger than its children, so we have to push 24 down. In this case, we'll switch it with 6, and then we'll switch it with 7, and so forth. The final operation is a decrease key operation. So suppose that, remember this tree was at 21. Suppose we want to do a decrease key on 21, and if we want to move it to 8. 21 right here is actually a pointer to that node right there. Suppose we want to reduce the key to 8. Well, we just go ahead and reduce it, and then we do the same thing we've always do, which is we bubble it up. So in this case, 8 is smaller than 9, so we do a swap. And we're fine. Okay? So that was a very quick overview. How long does it take to insert a node? Log n. Make q, let's not talk about that. How long does it take to extract a node? Also log n, because you pop off the top and then you have to percolate a node. How long does it take to decrease key? Log n, because all of these operations are percolations. So this is a reasonably efficient data structure, very simple to implement. And it's going to help us with Prim's algorithm. Later, we'll talk about even more sophisticated data structures like Fibonacci heaps. We talk about this in the grad version of this course, which do some more fancy operations to reduce these operations in amortized sense. But let's get back to Prim's algorithm. So what we want to do is make a queue with all the nodes in V. It turns out that you can make queue faster than you can do a make queue operation in order n time for these type of data structures. If you have n nodes, you don't have to insert them one by one. You can just bulk insert them, and so forth. So we're going to make a queue. We're going to set all keys to infinity. And then we pick some arbitrary node. Let's call that D. Okay. Okay. We're going to set the key of V. We're going to set that to 0. In fact, let me just, since I'm running out of time. So we initialize each node with an infinity key. We pick some starting node and set its key to 0. And then here's the main portion of this loop. While this queue is not empty, we are going to pull the smallest node from this queue and consider all of its neighbors. If this neighbor is already in the queue, then we're going to, in fact, all of them should be in the queue because we've inserted them right here. We are going to decrease key and set the new weight for this key, the new key value for this, to be the weight of the edge between the node we just picked and that current node. All right? So in these last 2 minutes, I'm going to simulate how we would run Prim's algorithm on this same data structure. So we start by picking some designated node D, setting that key value to be 0, and everything else was infinity as we started. We do an extract min on this queue. What's the minimum node? 0, because everything else is infinity. So this is the node that we extract. And now, in this loop right here, for every one of these neighbors, if the weight of the edge between those neighbors is smaller than its current value, which is infinity, so it is, we update them. So for example, in this next set, we would update the weight of this to be 5, 8, 7, and 8 based on the weights of these edges. And now these red arrows essentially help me keep track of the actual answer. In the end, the red answers that remain are going to be the ones that are part of the solution. So now in the next step, we're going to come back to the beginning of step 6 right here and extract a min. What node will I extract? This time I'm going to extract H, because this node is no longer in the queue. I already extracted it. And among the keys that you see, infinity, 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 8, 7, 8, 5, 5 is the smallest. And now I'm going to update all of its neighbors being 8, I, and F. Okay, both of these are infinity, so I'm going to update them. This one will be updated to 11. This one already has 8, so 9 is not an improvement. I don't do anything. This one was infinity. I update it to 6. And that leaves the tree in this format right here. Question? Yes, you can pick the starting node arbitrarily. You know that all of these nodes have to be in the tree at some point, so you can pick them at any spot and start. I will pick up with this on Thursday.